In this video lecture, we're going to discuss a couple of specific applications of conditions, which you should find useful in some upcoming assignments. Okay, let's get started. We've already seen that conditions are nothing but boolean valued expressions which are used to express decision-making in programs. There are 9 basic conditional operators grouped into 3 categories: 2 equality operators, 4 relational operators, and 3 logical operators. With the help of these last 3 logical operators, expressions involving these first 6 conditional operators can be, and often are, combined into more complex, compound conditional expressions. In the material of this lecture segment, we want to focus on 2 specific applications of conditions, ones which you'll probably be seeing in some upcoming programs. These are Boolean flag variables and a matrix of logical states. Let's take a look at each one of these now. First off, the idea of Boolean flag variables. Both conditional expressions and Boolean variables themselves are of the Boolean data type, and thus can be used interchangeably. In programming, you'll often hear Boolean variables referred to as flags or switches or settings. All this means is that they represent some simple on-off, true-false type of information. So in this code example on the right, we have these 4 Boolean condition variables and these other 2 Boolean flags with initial values as shown, which we might imagine to be some sort of program inputs. Then, in these examples which follow, each of these statement pairs represents 2 logically equivalent expressions. We can write an expression which checks whether this flag's value is true explicitly, or we can simply use the name of the Boolean flag by itself. Since this entire first expression evaluates to true or false, and this flag's value is either true or false, these 2 expressions are logically equivalent, but using the variable name alone is simpler and often preferred. In this next example, if the value of flag 2 is false, then this entire expression evaluates to logical true. But that's just identical to negating the variable itself from false to true, and so again, these 2 expressions are logically identical. But this second form is simpler and often preferred. You can write your conditional expressions in either fashion, but I think you'll come to find these second forms to be simpler and more typical in practice. As a reminder, we generally don't write and use conditional expressions in isolation like this. Instead, you'll generally always see them as part of larger logical structures, which we'll begin examining in our next lecture topics. Taking the prior example one step further, Boolean variables are no different from any of the other Java data types, and they too can be used as method inputs. So what we've done here is to take the prior code and turn it into a method by wrapping this method interface around it and carving out the 2 input flags and making them now the 2 inputs to this method. Now the previous code has become a method called doSomething, which takes 2 Boolean values as input. If we want to call this method from some client code, as we see up here, we simply specify the desired 2 true or false flag settings, and some action will or will not be taken inside this method based upon the values of these 2 Boolean flags. This method code is now making decisions based upon these 2 input Boolean switches. You'll be seeing this in an upcoming program. Here's another example of working with conditional expressions to specify some matrix of logical states. In the most general case, let's imagine that we have n completely independent inputs of some kind. Then let's imagine that the output is some prescribed function of those n inputs, or as a general expression, y is some function of the n inputs x1 through xn, as shown here. That seems kind of abstract, so let's make it a little more real and tangible. Let's imagine that we're working at some software company and we need to realistically prioritize our efforts to respond to our customers based upon each client's importance and the urgency of their issues. We might imagine a matrix of possible combinations, such as the one shown up here on the right. The 2 axes represent our 2 independent inputs, importance and urgency, on a scale from 1 to 5, with 5 being the highest. Then we might imagine some predetermined color-coded range of responses, as we see here on the right: critical, high, elevated, routine, and low. So each possible combination of importance and urgency will map to some specified response times. For example, some issue involving a priority 5 client with a priority 5 issue will of course receive our critical attention, whereas a priority 2 client with a priority 2 issue will receive a routine response time, whatever that might be. Or we might imagine this to instead describe our prioritization for fixing bugs in our product, where now the two independent axes might represent revenue impacts on the top and issue severity on the left. Just so you don't think this is arbitrary and made up, these kinds of business determinations really do take place internally at companies. Since there's never enough time, money, or people to do everything you want, some kind of prioritization has to take place. Here's another similar example. The Department of Homeland Security used to determine and publish a color-coded threat matrix, although this has been replaced by other types of updates. I have absolutely no idea how this was determined, but somehow all available data was rolled up into one of these 5 overall color-coded states. Same idea as above, though synthesizing much more input data. Okay then, going back to this first example, how would we implement something like this using conditions? Fundamentally, what we have here on the right is a 25-element table of logical states, where each state is one of 5 possible output conditions, as shown here to the right. Each of the 25 states is uniquely determined by the same 2 inputs, client importance along the top axis and issue urgency along the left axis. What we need to do then is come up with 5 conditional expressions that describe the situations for which each one of these is true. Each one of these states is mutually exclusive with the others. What we mean by that is, if the state is of one value, it cannot be any of the other 4 values at the same time. So for example, if the state is R or routine, that means it cannot be critical, high, elevated, or low. As you might have guessed already, each of these states on the right can be determined by some conditional expression which is dependent on the 2 inputs. To determine the conditional expressions that we need, it's important to keep a few things in mind. First of all, there's no one unique right answer for any of the conditions. They can be expressed in any number of ways, provided that they yield the right result. However, some expressions may be more easily formulated or understood than other ones. The conditions don't have to be determined in any set order. For example, in the order shown up here from critical down to low. In fact, it's best to look for larger, simpler, more contiguous logic combinations and express those first. Then we can express some of the later conditions in terms of not being some of the earlier conditions. And finally, it's okay to have some overlap or duplication as we express our conditions. Let's make all of this more concrete by looking at one possible implementation of the needed 5 conditions. Up here, we have our 2 integer inputs for importance and urgency, and we assume these are provided to us somehow. Next, we declare 5 named boolean variables to represent the needed 5 conditional expressions, the 5 possible states. Then looking at this table, I'd say the easiest condition to express is the one for this bottom row, where the low state is true if the urgency only is equal to 1, and it's completely independent of the importance. So here, if we compare the urgency to 1 and that condition is true, the low condition is equal to true. Otherwise, it is false. Notice that although the low state is the last one in this list up here, we've implemented its conditional expression first because it's easiest to express and we don't have to go in any prescribed order. Next, let's take a look at this blue region for which the routine state is true. This becomes the union of 2 regions, as we see here in this next conditional expression. The urgency is equal to 2, or the importance is less than or equal to 2, but not this low state. Notice how here we can make use of the low state since we already have an expression for that. Next, let's jump to the upper left-hand corner, where we see that the critical state is the intersection of importance equal to 5 and urgency equal to 5. Again, notice that we're jumping around in the order, but that's okay. Next, let's implement the high state, which we can see is this upper left region in orange, where both the importance and the urgency are greater than or equal to 4, but not this one critical state. We see this conditional expression implemented here, and it's a three-parter. Urgency is greater than or equal to 4, and importance greater than or equal to 4, and not the critical state. So again, we're making use of a previously determined condition here. Finally, we implement the elevated state, which we can see as this larger upper left corner in yellow, where the urgency is greater than or equal to 3, and the importance is greater than or equal to 3, and it's not the high state, and it's also not the critical state. Again, we can make use of previously determined conditions here. So now we're done. We can express these 5 conditions in any order, but we did so by expressing some of the easier conditions first, going after the low-hanging fruit first, then incorporating earlier conditions into later conditions. This was one possible implementation, but there are clearly other ways of doing this. It doesn't matter how we do this as long as we get the right results. Finally, how would we go about testing these 5 conditional expressions? What you would want to do would be to display these 5 Boolean results and test them out for a handful of input combinations. However, I do recommend that you display them in some logical order. For example, in this state order shown up here on the right. This output code at the bottom shows how you might do that. It prints out all 5 labeled Boolean values, tab-aligned as usual, and each one on its own line using these new line control characters. For each input combination, only one of the conditions can be true, and all the other conditions must be false. Okay, so now we've seen the process of how we might go about implementing 5 logical states like this, using conditional expressions. Please look this example over carefully, because you may be seeing it soon on a program assignment. And that's it for this topic.